Hi everyone, and welcome to the ONF Spotlight event. I'm Carmelo Gascona, a software engineer at ONF, and today I'll be joined by Stephen Ibanez. Stephen is a PhD candidate at Stanford University working with Professor nanoPU. He has a passion for both research and teaching. His research interests include high-performance network system, computer architecture, and distributed application. Today, Stephen will talk about a very interesting topic, nanoPU, an exciting project that aims at building a new processor for highly parallel workloads. The main idea behind nanoPU is that of rethinking the CPU network interface to be able to move messages from the network wire to the CPU with the lowest latency possible. Without further ado, welcome, Stephen. Please take it away.
All right, great. Thank you, Carmelo. So like Carmelo just mentioned, today I'd like to tell you about a project that I'm working on along with my colleagues at Stanford, Alex Mallory, Serhat Arslan, Theo Jepson, Mohammed Shabazz, Chang Kim, and Nick McEwen. So this talk is going to be about a new processor that we're building called the nanoPU, which aims to accelerate applications that utilize tons and tons of extremely fine-grained RPCs. And it does this by enabling super low and predictable RPC latency. So let me briefly introduce the types of applications that I'm talking about. So researchers have demonstrated that by harnessing thousands of cores in parallel, the runtime of highly parallelizable applications like video encoding, object classification, software compilation, and MapReduce style analytics can be reduced from hours to just minutes. So for example, XCamera from NSDI 2017 demonstrated that by harnessing almost 4,000 cores in parallel, video encoding time can be reduced from 2 hours on a single machine to just 2 minutes. So that's pretty dang impressive. But it does beg the question, why only 4,000 cores? Why not 400,000 cores? These applications can certainly benefit from harnessing more parallelism. And if we divide up tasks with such fine granularity that the working set of each task is cache resident, then we can expect significant reductions in application completion times. So we call these tiny fine-grained sub-microsecond tasks nanoservices. And we define nanoservice applications as having the following characteristics. They're highly parallelizable into fine-grained nanotasks that are communicating via RPC. Each of these nanotasks processes network messages in 1 microsecond or less, and each nanotask usually maintains a cache-resident working set in order to avoid expensive memory accesses. And while it still remains to be demonstrated, perhaps a nanoservice deployment would be able to achieve millisecond scale completion times. So this is the class of application that we're aiming to enable and accelerate with the nanoPU. So why don't nanoservice applications exist today? Well, that's because this approach of trying to harness hundreds of thousands, maybe even millions of cores in parallel has a really big problem that we need to solve, RPC tail latency. And tail latency refers to the latency of the slowest requests, that is the latency at the tail of the distribution. And the reason tail latency matters so much is because we have to wait for the slowest request to complete in order for the application to complete. So the application completion time is very sensitive to the tail latency. So let's take a look at some concrete numbers. So consider a hypothetical system where each server usually responds in 1 microsecond, but has a 99% tail latency of 100 microseconds. So that is, if we run the application using just one server, then 1 in 100 times we run it, it'll be slow. That is, it'll take 100 microseconds or longer. So what happens to the application completion time as we try to harness the computing power of more servers in parallel? So let's take a look at a plot. So on the y-axis is the probability that the application will take longer than 100 microseconds to complete. And on the x-axis is the number of servers that we harness in parallel. So we see that even if we try and use just 100 servers in parallel, there becomes a 63% chance that the application will take longer than 100 microseconds to complete. So if we can reduce tail latency, then we can harness more servers in parallel while keeping application completion times low-ish. I say low-ish because even if we're able to reduce 99.99% latency to 100 microseconds, then there's still almost a 20% chance that the application will be slow when scaling to just 2,000 servers. So in order to harness like millions or hundreds of thousands of servers, we really need to drive the tail latency way, way down. Okay, so let's get to the problem at hand. So what causes high RPC tail latency? Well, in general, tail latency usually manifests when we have some critical shared resource, and then we do a poor job scheduling access to that resource. So in particular, the resources we care about are network fabric resources, CPU cores, host memory bandwidth, and cache space. And frankly, modern systems are ill-equipped to efficiently schedule access to these resources for network-intensive workloads. So to explain why, I'll briefly walk through the steps involved in processing an RPC request on a modern system. So when a client sends a request to a remote server, the transport logic splits the request into one or more network packets and then schedules those packets on the network fabric resources. And suboptimal congestion control policies like TCP are in widespread use today, and TCP is very ill-suited for low latency RPCs for a whole bunch of reasons. TCP causes large queuing delays and packet loss, which can inflate the latency through the network by milliseconds. And since TCP is connection-oriented, it can cause short messages to get queued behind long messages, increasing tail latency. Now, researchers have recognized these problems and have proposed a number of new and improved transport protocols like NDP, HOMA, and HPCC, which are much more well-suited to provide low latency through the network. However, these protocols are implemented in software today, making it very challenging for them to keep up with increasing network speeds. So our goals are twofold. One, to provide a programmable platform that will allow network operators to deploy any of these high-performance transport protocols, and two, enable this logic to run in hardware rather than software. Okay, so now let's take a look at what happens when the packets of a message arrive at the server. So when the packets of an RPC request arrive at the target server, the NIC uses a technique called receive side scaling, or RSS, to try and load balance packets across the cores that are used to implement the transport processing. RSS operates by hashing some packet header fields and then assigning packets to cores based on the hash result. And in practice, this doesn't always work particularly well, and sometimes packets are still sent to heavily loaded cores, resulting in high tail latency. But once the NIC decides which cores to dispatch the packets to, it uses direct memory access, or DMA, to transfer the packets over PCIe into host memory, or it might use direct cache access to place the packets directly into the last level cache. And this actually leads to another source of resource contention, and hence tail latency. Network traffic has to contend for cache space and memory bandwidth with applications, which causes significant variability in message processing times. And this problem is really exacerbated as network speeds continue to increase. Now, after the transport logic processes the packets and produces a message, there's typically another load balancing decision to try and balance messages across the application cores. Now, throughput is a concern here because small RPC messages can arrive on a 100 gig link at 195 million requests per second, whereas a single core can only process up to maybe 10 million requests per second, so only about 5% of the network capacity. So, and then there's the thread scheduling decision. In order to try and make efficient use of the CPU cores, a thread scheduler will try and multiplex various application threads on the cores. However, the problem is that these software-based thread schedulers operate at very coarse granularities. In fact, even if they were to make thread scheduling decisions every, say, 5 microseconds, which is the time slice of state-of-the-art operating systems, it's still too coarse-grained when RPCs are processed in less than 1 microsecond. So because of this, today's best practice when deploying a latency-critical application is to dedicate cores for use only by that one application, such that it's never swapped off, it's always running and ready to go. But in my opinion, this is a cop-out solution and is a very expensive one too, because it means cores are not efficiently multiplexed and CPU resources are wasted. But eventually, the application will produce a response message which is turned back into packets, and those packets go back over the memory hierarchy over PCIe to the NIC and out into the network. So now, to give you a sense of performance, the minimum wire-to-wire latency that we're aware of, which measures the time from the wire to the application and back to the wire, is reported by ERPC to be 850 nanoseconds. Wire-to-wire tail latencies on modern systems can easily exceed tens or even hundreds of microseconds. So in contrast, we're aiming to bring the minimum wire-to-wire latency down to below 100 nanoseconds and tail latency to just 1 or 2 microseconds. Now, if we look at the system design that I just described, it's pretty clear why tail latency is such a problem. Network data has to go through the NIC through PCIe, through memory, cache, and up to 2 cores before even reaching the application. There are just so many layers of processing and queuing, so many opportunities for resource contention and inefficient scheduling decisions. But at the end of the day, the goal that we're trying to accomplish is really dead simple. Just move data between the network and the applications while ensuring that the cores are used efficiently. So what we really want is for the NIC to take care of translating between packets and messages, as well as efficiently load balancing messages across cores. What we want messages to get delivered directly to applications running on the cores rather than via the memory hierarchy. And we want applications running on the cores to be multiplexed with such fine granularity that their performance of the high priority applications is basically unaffected, even when the core is shared with lower priority applications. So this is exactly what the nanoPU is designed to do. Now, I just said a lot of things, so let's break this down. But first, let me redraw this picture so we can focus on the things that we care about, namely the NIC and the cores. So we're briefly going to build the nanoPU design together. So first, let's focus on this direct path from the NIC to the application running on the core. There are 2 main reasons why we would want to do this rather than going over PCIe and through the memory hierarchy. First is that it would allow us to literally shave hundreds of nanoseconds off the minimum wire-to-wire latency, bringing it down to below 100 nanoseconds. And secondly, it avoids causing contention for cache space and memory bandwidth with applications, thus reducing tail latency. Okay, so this sounds great, but how would this even work? And what does it even mean to feed network messages directly to applications running on the cores? Well, to make this work, we're going to gain inspiration from a design that was proposed 31 years ago. So back in 1989, Bill Daly and his colleagues built the J machine, which performed on-chip intercore communication by sending messages directly through the CPU register file. That is, an application sent messages by writing 1 word at a time to a particular CPU register, and those messages were launched directly into the network without ever going through host memory. So nice, this sounds like what we want. So let's go ahead and try and give it a shot. To explain this, we're going to zoom into one of these cores. So here's one of those cores with the register file, the CPU pipeline, and the L1 caches. We're going to repurpose 2 general purpose registers for network I/O and call these netRx and netTX. And when an application issues an instruction that reads from netRx, this is actually going to read the word that's at the head of the network receive queue. And similarly, when an application issues an instruction that writes to netTX, this is actually going to write a message word to the tail of the network transmit queue. Okay, but how does an application know when it has reached the end of a received message? And how does the hardware know when the application has finished writing a message? Well, we can make the first word of each message special and have it indicate the message length. Okay, so sweet, this is looking pretty good. And hey, look, we don't even need to modify the compiler at all because we can just tell GCC not to use our 2 reserved registers when we're compiling the application. So this means we can now write a simple loopback application that echoes received 3-word messages back to the sender with literally 3 instructions: move from netRx to netTX, move from netRx to netTX, move from netRx to netTX, which on a 3 gigahertz processor takes just 1 nanosecond. And for reference, that's about how long it takes to access the L1 cache. Okay, so at this point, you might be wondering, this seems too simple, maybe even too good to be true. So what's the catch? Well, I'm glad you asked, because up to this point, we've been making a pretty major assumption, namely that there's only 1 thread running on the core. So what happens when there's 2 threads running on the core? A low priority gold thread and a high priority latency critical green thread. Let's say the gold thread is currently running on the core processing a message, and then a message arrives for that high priority green thread. So what happens now? Well, one option is to wait around for the operating system to come along and schedule that high priority thread onto the core so that it can process its message. But as I said before, modern software-based thread schedulers are too coarse-grained. We don't want to wait for the operating system to make thread scheduling decisions. A high priority message just arrived, and we want to start processing it right now. So in order to enable this, let's add a hardware thread scheduler to the core. This thread scheduler is going to monitor the priority of arriving messages, as well as the status of the threads, and will tell the operating system exactly when to perform context switches between threads by firing interrupts. So in this case, the thread scheduler will immediately fire an interrupt after that message arrives for that high priority green thread. And the nanoPU's minimal operating system, which we call the nano kernel, performs a context switch by storing the gold thread state into memory and loading the green thread state from memory, all of which can happen in just 50 nanoseconds on our RISC-V prototype. Okay, great. So now the green thread is running on the core and it's ready to start processing its message. But wait, the gold thread's message is still sitting there on the head of the RX queue. So how the heck are we going to process our message when this message for a different thread is in the way? So this is exactly the problem that the J machine ran into back in 1989. It's really hard to prevent one thread from accidentally or maliciously processing messages that are meant for another thread. So this is a huge problem, and we need to find a way to fix it if we want to have any hope of using this register file network interface. Fortunately, Moore's law has helped us here. From 10 to the 6 transistors per chip back in 1989 to over 10 to the 10 today, we can now afford to dedicate additional hardware for this purpose in a way that was not feasible at the time of the J machine. So in order to overcome this issue, instead of using a single RX and TX queue, we will use separate RX and TX queues for each thread that's running on the core. And the hardware is going to ensure that each thread can only read from and write to its own queues. So now the green thread can process its message without anything else getting in its way. So this seemingly simple change enables us to use the register file interface in multi-threaded environments. And this is something that has been considered impractical for decades. Okay, great. So now we've got the CPU network interface figured out as well as how we're going to schedule threads on the cores. So it's important to emphasize that these are messages that are being passed to and from applications via the register file interface, not Ethernet frames or IP packets. So in order to provide this interface, this means that we have to implement the transport layer in the NIC hardware. So let's take a look at that next. So I should start by saying we're definitely not the first to suggest implementing transport in hardware. In fact, modern NICs that support RDMA already essentially do this. And also Tonic, which is a recent NSDI paper, proposes a set of useful building blocks that can be used to implement transport in hardware. And we gained some insights and inspiration from this work. So why is it important to move transport logic into pipeline hardware? Well, because here it can run at line rate, freeing CPU cycles to focus on what it should be doing, running application logic. And also it can run with super low latency. For example, our hardware NDP implementation runs deterministically in just 7 nanoseconds for each packet. Okay, so how is the transport layer implemented? Well, explaining the precise details is beyond the scope of this talk, but I'll give you a high-level overview. So let's first take a look at the hardware interfaces of the module. So the external interface to Ethernet is packets, and the internal interface towards the core is messages, that is RPC requests and responses. One of the main things the transport module does is packet processing. So as such, it contains P4 programmable ingress and egress PISA pipelines that are used to process packet headers like VXLAN, overlay tunnels, and telemetry data. And it's also used to implement congestion control. Since these pipelines are programmable, network operators can deploy custom transport protocols that are well suited for their specific workloads and networks. Now, the other main task performed by this module is to convert between packets and messages. So to do this, it contains a reassembly buffer to reassemble packets which might arrive out of order into messages, and a packetization buffer to split messages into packets, which might in turn need to be retransmitted out of order due to packet drops in the network. In terms of the interface provided to applications, the nanoPU's transport layer provides the abstraction of reliable one-way message delivery, as opposed to the more traditional reliable long-lived bidirectional byte stream provided by protocols like TCP. And this approach is nice because it enables an efficient hardware implementation by reducing state requirements. The NIC only needs to maintain state for each message as it is currently being delivered, and it does not need to maintain any persistent connection state, which is really nice. Okay, great. So now we've got the transport logic and the processing on the core all set up and ready to go. So the next major problem to tackle is how are we going to load balance messages across cores? Well, if we just randomly send messages to cores, then some messages could end up sitting in a queue waiting for a busy core when there's another core that's just sitting idle. So we need to avoid that situation in order to minimize tail latency. So for this aspect of the nanoPU, we gain inspiration from a recent system called Nebula, which demonstrates that efficiently load balancing RPCs across cores can be efficiently implemented in hardware. Unfortunately, I don't have time to describe the details now, but I will say that this line rate load balancer in our RISC-V prototype can schedule messages across cores at a whopping 390 million requests per second. And load balancing decisions are made in less than 1 nanosecond. So with that, we filled in the final missing piece of the nanoPU design. And I'd like to emphasize that we've put the transport logic in fixed latency hardware, the load balancing logic is in fixed latency hardware, and the thread scheduling logic is also in fixed latency hardware. So it should be pretty obvious that this design is able to provide extremely low tail latency. So we built a prototype quad-core nanoPU with a 200 gigabit per second network interface based on the open source RISC-V Rocket Core. And a block diagram of the prototype is shown in this figure here. The Rocket Core is a simple 5-stage in-order single-issue processor, and it required very few modifications to add support for the nanoPU's register file network interface. Our prototype runs a custom-written nanokernel consisting of about 1,200 lines of C code and RISC-V assembly instructions, and we configure the nanoPU's programmable transport module to implement NDP, which is a recently proposed data center transport. To evaluate our nanoPU prototype, we run it on FPGAs in Amazon Cloud using FireSim. And FireSim is great. It allows us to run large-scale, cycle-accurate simulations of applications using hundreds of nanoPU cores. The FPGAs run at 90 megahertz, and we simulate a target clock rate of 3.2 gigahertz. And all the results that I'll present are in terms of this 3.2 gigahertz target clock rate. So this figure here shows the latency breakdown for a single 8-byte application message measured from the Ethernet wire through a simple loopback application on the core and then back to the wire. Our prototype does not include the Ethernet MAC in serial I/O, so we instead measure the latency of this module on a commodity 100 gig switch and then report that value here. So the wire-to-wire tail latency is just 65 nanoseconds. For reference, that's about how long it takes to travel 20 meters at the speed of light. For comparison, RPC, which we believe to be the current state of the art, reports a wire-to-wire tail latency of 850 nanoseconds, or about 13 times higher than the nanoPU. And in fact, if you look at the latency breakdown, you'll see that the majority of the nanoPU latency is due to the Ethernet MAC in serial I/O. Without it, the loopback latency is just 13 nanoseconds. So we believe this is, by a pretty large margin, the lowest latency Ethernet NIC ever designed. Furthermore, using this register file interface, it's possible to design applications running on a single core with a throughput of up to 200 gigabits per second. That's about 2.5 times higher per core throughput than RPC. Okay, so here we evaluate the performance of the nanoPU's hardware thread scheduler against a more traditional timer interrupt driven thread scheduler. A single core is configured to run 2 threads, one that's running with high priority and the other with low priority. Each thread processes a request for 500 nanoseconds and then sends a response back to the sender. We use a custom load generator, which generates 10,000 requests for each thread, which are randomly interleaved, and measures the total time until the response is received. The timer-driven scheduler performs context switches between threads at 5 microsecond intervals, which is the time slice of state-of-the-art operating systems. So this plot shows the 99% tail latency versus load. An ideal system would be able to process 2 million requests per second because each request has an on-core service time of 500 nanoseconds. So at relatively low load of 50%, the nanoPU lowers tail latency of the high priority request by 4 times to just 1.4 microseconds, and it lowers tail latency of the low priority request by 6.5 times to 3.2 microseconds. We also see the nanoPU is able to achieve at least 96% load with a high priority tail latency of 2.1 microseconds and a low priority tail latency of 18.2 microseconds. And these results shouldn't really be surprising because whereas the timer-driven scheduler has to wait for 5 microsecond boundaries to swap between threads, the nanoPU scheduler ensures that the high priority thread is always running whenever it has a message to process, and the low priority thread is able to run whenever the high priority thread is idle. We also evaluated additional aspects of the nanoPU, such as its ability, the ability of the NIC to load balance messages across cores, as well as the NDP hardware implementation. For the sake of time, though, I'm going to skip over these evaluation results. I'd also like to mention that we've ported a number of real applications to run on the nanoPU to take advantage of the extremely low latency. So Mica is a high-performance key-value store, and we needed to modify about 36 lines of functional code to optimize Mica to run on the nanoPU. And after doing so, we found that it was able to support sub-microsecond 99% tail latencies for GET input requests. We also implemented both chain replication and raft consensus for fault-tolerant replication of state machines on the nanoPU. So I'd like to wrap up with a brief discussion of how ideas from the nanoPU might be adopted by industry in the future. So one possibility is to deploy a whole cluster consisting of hundreds of thousands of nanoPUs, which are just dedicated to processing low latency RPCs. And this could be ideal infrastructure for deploying the nanoservice applications that I described at the beginning of this talk. Each nanoPU could be packaged like a conventional CPU with, say, 1 to 200 cores and a 100 gig network interface, although in this case, the network interface could become a throughput bottleneck. So to overcome that issue, another possibility is to package the nanoPU more like a switch ASIC with, say, 512 cores, 256 100 gig interfaces, and some SRAM, which would be about the same package, power, area, and pins as a modern switch ASIC at 25 terabits per second. So if all RPCs are processed in, say, 500 nanoseconds, then this device would be able to process over 1 billion RPCs every second when using nanoPU cores. If we were to instead use something like eRPC on this, the software overheads involved in processing RPCs would limit throughput to something more like 500 to 800 million requests per second. Alternatively, nanoPU ideas could be incorporated into the design of general purpose CPUs to accelerate processing of latency sensitive RPCs. In addition to the nanoPU's fast path through the register file, this design would probably also include the more traditional DMA path into memory for data that does not need to be immediately processed by the CPU, such as for RDMA applications. And a fourth possibility is to use nanoPU ideas on a SmartNIC. So modern SmartNICs already have many cores on them and are used to offload various processing tasks from the host CPU. And one potentially appealing alternative here is to instead use nanoPU cores rather than traditional cores, which would allow them to process network data much more efficiently and can potentially even be used to allow cloud providers to offer an ultra-low latency RPC service. So the key takeaway from the nanoPU is that if we truly want to minimize average and tail latency, then we need to, 1, bypass the memory hierarchy and add a fast path directly from the network to the heart of the CPU pipeline. And 2, we need to move all of the key resource scheduling decisions from software to hardware, namely transport, load balancing, thread scheduling, where these algorithms can run with lower latency and variability, higher throughput, and operate more efficiently. That being said, the nanoPU is not a silver bullet. There are still challenges that will need to be overcome. For example, we need to rewrite applications to use the nanoPU's register file network interface and the message-oriented transport API. And we also need to figure out what the register file interface looks like on more sophisticated processors than our single issue in order Rocket core. But that being said, I'm looking forward to facing these challenges as well as others that arise in the future. Thank you.
All right, thanks, Steven. Really great presentation and work. I really appreciate how you explain how things work today, how we move packets from the wire to the CPU. And actually, how can we make things better by almost taking a clean slate approach, like remove everything that is in the middle and just use the register file.
Yeah.
I mean, it's a very simple and powerful idea. And you mentioned at some point that similar ideas were explored in 1989 with the J machine. But you know, a long time passed since 1989. I wonder if how come are we just proposing now to use direct access to the register file? And if you can just reiterate on the challenges that prevented us from doing it before.
Yeah. So this register file interface has been used in the past before. So like decades ago, like I mentioned in the talk, the J machine used it. There was also other processors like the Cray T3E and the RAW processor from MIT that also use this register file interface in the context of low latency HPC systems. And it also has shown up more recently, like in 2004, with the Snap processor in the context of wireless sensor networks. And there, the key thing is power. And latency also comes into play there because they wanted to use the register file interface to minimize the amount of time the CPU has to be active and consuming power. And so this provides the lowest possible latency. But the key challenge that has never really been overcome when using this register file interface is how do you use this in the context of multi-threaded environments where you have multiple threads and you need to isolate the network I/O amongst all these threads that are sharing the CPU core. And decades ago, it wasn't practical to add additional support into the hardware to perform this isolation. But now, since Moore's law has advanced and we can fit much more transistors onto the chip, we can actually dedicate additional hardware for this purpose. And this makes it feasible to use the register file interface in multi-threaded environments. And so really this register file interface shows up whenever low latency is needed. And now everyone's talking about how do you minimize latency for RPCs. And so here it is again.
And it seems that the thread scheduling policy is based on this idea of like having queues and having someone allocate messages into these queues. I just wonder, is there any like challenges that comes from supporting like a big number of queues, or like what is the right dimensioning for the system to be able to use like for real application? Is it enough to just have two queues, high priority one, low priority one? Are we supposed to have one queue per application?
Yeah, so that's a good question. Basically the queues have to fit like the one maximum size message for each thread that can fit. So that dictates how much memory you need to allocate for these queues. So there's probably like a nanoPU processor. If you're trying to dedicate hardware queues for each thread that's running, you're probably not going to be able to run as many threads as like a software-based thread scheduler, but you're going to be able to multiplex those threads on the cores much more efficiently. So in the context of super latency sensitive applications, where the best practice today is to just dedicate one thread to each core, this is going to provide much more efficient multiplexing of those threads on the cores. So it makes it practical to run multiple latency sensitive threads on the core and multiplex them very efficiently.
Right. So another question is that you're describing nanoPU as a processor like targeted for nanoservice applications, right? But it looks like the same idea can be used for other applications as well, existing applications from the basic, this simple packet processing. Just let's use a general purpose CPU to process packets. So I wonder if you're considering like other applications other than nanoservices.
Yeah, so we're focusing on nanoservices because these applications have the characteristics that best exploit the features provided by the nanoPU, the cache residency, the small message processing time, and so where you really need to optimize the latency of the network. So these are the applications that we think will like best highlight the benefits provided by the nanoPU. But definitely, I think you can like existing applications will probably also provide it'll provide lower latency for them as well. So for example, like Mica and chain replication and Raft are three existing applications that we've ported, and they provide we've seen some performance benefits there. But that being said, like not all networking applications are going to want to use this register file interface. Like if the goal of an application is to move a bunch of data from its own memory to the memory of another machine, like you don't want to force all of that data to be touched by the CPU pipeline. In that case, it's better to just use like DMA or RDMA. So really, that's why I said if you were to incorporate these ideas from the nanoPU into a general purpose processor, you'd probably have both paths, the path through the register file interface, as well as the more traditional DMA, RDMA path into memory.
Um, so one other question I have is one slide you showed like the architecture of the nanoPU with a P4 programmable PISA pipeline at the beginning. And you said that we can use this pipeline to do the basic layer 2, layer 3 functions, but as well as implement like congestion control and transport protocols in general. Can you tell us about the challenges implementing transport protocols in P4? Is it possible to implement any transport protocol?
Yeah, that's a good question. So yeah, really the main challenge with implementing transport protocols in hardware is handling the shared state requirements where you have independent events that all want to update the same state. And really the handling of state is outside the scope of P4. If the architecture provides a means to update shared state or state variables, then really the P4 logic can control the vast majority of the transport logic. As long as the architecture provides that means, then you can describe the vast majority of the transport logic in P4. The challenge here is to develop that architecture that can support the state requirements. But fortunately, this is easier made easier because of two things. One of those things is the trend away from connection-oriented transport protocols to message-oriented transport protocols like NDP and HOMA. And these protocols, they're proposed because they can provide lower tail latency. You don't have this issue where short messages are getting queued behind long messages. Since each message is treated independently, short messages can bypass long messages. You can implement something like SRPT and get lower tail latency through the network. But another key benefit of these message-oriented transport protocols is that they have smaller state requirements. So it becomes much more practical to implement them in the NIC hardware, because these protocols, they only need to maintain state for each message as it is currently being delivered. And then once that message gets successfully delivered, then it can completely forget all that state. So it can free that state. So it doesn't need to maintain any persistent connection state, which means that like the scalability is limited by how many messages you have outstanding and not by how many hosts you want to talk to. So that's like a key benefit of these message-oriented transport protocols. And so that's why the API that the nanoPU transport layer provides to applications is one-way reliable message delivery as opposed to like long-lived connections. And the other thing that is that NICs have to maintain or have to process packets at lower rates than like multi-terabit per second switches. And so it's much more practical to have multi-ported state in a NIC than it is in like a switch. So that's definitely something we take advantage of.
I guess, so is one of the goals of the nanoPU project also to come up with a P4 architecture that is well suited for the implementation of transport protocols? So you mentioned as long as you have an architecture that offers you the primitives to do they provide the state access requirements you were describing, then it's easy to implement transport protocols. So is that a goal of the nanoPU project?
Yeah, it is. So we have we have the baseline architecture right now, and we have it implementing NDP, and we're in the process of porting HOMA to work on this architecture as well. And so yeah, you can expect a paper to come out about that at some point.
Nice. One more question. Right after the PISA pipeline, there's a message reassembly buffer, right? I'm wondering, is that a fixed function block? Is there an opportunity to make that programmable? Does it make sense to make that programmable? What are the challenges?
Yeah, so that element is it's pretty simple. It's just like it's a bunch of fixed function or fixed buffers, fixed size buffers. And when the first packet of a message arrives, you allocate a buffer, and then you just slot packets into at the right offset. And so that in itself is a pretty simple thing. I can imagine there being reasons why you might want to make it programmable. Like for instance, DPDK has this notion of generic receive offload, and you have like the programmer can write some custom function that reassembles packets in some way. So that is an interesting an interesting suggestion that honestly I hadn't really thought of before. But perhaps that's something that can be made programmable in the architecture. Somehow writing some P4 logic that will reassemble packets in some custom way so that all of this data gets delivered to applications in one go. That's something we can explore, definitely.
We suggest that right now the design is very simple. We just have a number of buffers, and then it's up to the pipeline to decide where to essentially where to store segments extracted from packets based on information on the packet header itself.
Yeah, right. Yeah. So the transport layer has the message ID and it has the packet offset. And so there's like a table that keeps track of whether or not a buffer has been allocated for this message. And then if it has, then it looks at that pointer and then slides the packet into the correct offset, basically.
Amazing. All right. I'd like to thank Steve for the time and the representation. I guess one last question. What comes next for the nanoPU project?
That's a good question. Yeah, so we're really interested in exploring these nano service applications. So like the types of applications that I mentioned at the beginning of the talk which are like very highly parallelizable into fine-grained tasks with cache resident, lots of RPCs being thrown around. We're also looking to gain inspiration from the HPC community, so like n-body simulations, physical simulations, and also from the graphics community, like distributed ray tracing. So these are all like very highly parallelizable applications. And I'd love to like run a large scale nano service application on our simulation infrastructure on Amazon Cloud with these with FireSim. So that's one thing I'd love to do. The other thing I'd love to do is to actually like build the nanoPU ASIC, like turn it into real silicon, either like as a SmartNIC with nanoPU cores on there, or like just maybe even just one nanoPU core with 100 gig interface and just have it dedicated to processing low latency RPCs. I think it would be a really fun experience.
Right. Yeah, really looking forward to that. All right. Thanks, Steve, for joining us today.
Thanks.
Yeah, thanks to the audience, and make sure to check out the other recordings in the Spotlight series. All right. Take care. Bye-bye.